All right. So we've been making carbocations today by reacting alkenes with strong acids like HCl. You make a carbocation, major, major, and minor. If finally we can understand why now. Why is this the major cation? Tertiary is going to form a lot faster than secondary. So I would expect if you were asked to circle the major product, you'd circle this one. If you were asked to explain your circle, you'd say, don't you dare talk about the two products. This has nothing to do with the products. This is the intermediate. The carbocations are the hardest things to make here. So you need to talk to me about this carbocation because it's tertiary. It has more hyperconjugation than this carbocation, which is secondary. So it will form faster. If it's forming faster, you're making more of this in the same amount of time as you're making this. That's major versus minor, right? Same story over here. Well, it wasn't there. It was here. No. Did I not go back far enough? Where's my water one? Is there no activity 3 on here? Scroll up on this one. Oh, thank you so much. Yeah. And yeah. So yeah. Carbocation major, minor, same logic, right? When do you get them? Alkene plus strong acid. So don't talk to me about carbocations unless you have an alkene and a strong acid. We'll be doing a lot of mechanisms that don't have that combination, and you won't be talking about carbocations, okay? But today I've planned it. All day today is carbocation day. And all day next Wednesday, this is 2 days, it's called triangle day because we're going to have triangle intermediates. No triangles today. Okay. So I'm grouping mechanisms in terms of things they have in common. Try to make it easier because it's right now it's just like, what is he doing? Everybody should be there right now. A weird feeling in your stomach and what the heck is he doing? Everybody has the same thoughts. No, it's not just you. Okay. All right. And the only way to learn these is by doing them by hand. There's a physical connection. There really is. You can't look at them and learn them. So the journal is a trick by me to get you started. Okay? The journal list is on the syllabus, and I need one entry for each item on that list for material on that current test. So you would start in 6, do 6.1a. If there's an item listed 6.1a, copy the item, give me an entry, straight from the textbook's good, or the lecture notes. But then in the lecture notes, you got to find them. Textbook, you know they're there with the section number. That's why I prefer that. And that's the first mechanism you do. That's just getting started. If you haven't done 10 more by the time the exam comes in the same type of reaction, you're not studying properly. The only way to do it is to do many, one after the other, and then finally realize I've been doing the same thing 5 times in a row. Okay, until you realize that, you think every time you do it, it's a different mechanism. You got to get past that. We had a question? No, we're good. Thank you. So one thing you don't know about carbocation rearrangements is that if a carbocation can rearrange to get a more stable carbocation, then it will. But you have to know what you're allowed to do during a rearrangement. And Control T. During, my typing's getting worse. During a rearrangement, nice, I got the caps lock on. An atom, either C or H, from an adjacent carbon to the carbocation can bring its electrons towards the carbocation carbon. So that's how it works, only one being carbon. Well, I guess that's the whole thing. Okay, make sure that's big, bigger. Yeah, purple. There we go. During a rearrangement, add atoms from an adjacent carbon. Move everything down. Okay. Now, this is good time to review stick figures. Tell me what atom moved and from where? The hydrogen from which carbon number if you're numbering from the left? I know it's not nomenclature, but 2. He knows his stick figures well enough to know that there was 2 H's on this carbon and only 1 H on the same carbon over here. Yeah, he knows that. So he knows one of them moved. And this carbon now has how many H's? 2. How many did it have before? 1. Yeah. Moved from here to there. Show it like this. Draw the H. And look, it followed the rules of arrows. It started at a sigma bond and ended at a carbon atom. And you want to see the H? I'm going to draw it temporarily. There it is. We don't need to show it. Yes?
Why did it do that?
It actually would not do it because we did not get a more stable carbocation. That's part of this exercise. Yeah, I'm going to show you how they happen, and then I'm going to tell you when they do and when they don't. And there's no motivation at all to go from secondary to secondary, so it does not happen. Does that clear? That doesn't happen? That's what that means? If it doesn't get more stable, don't do it.
So if it was turning from this side to that side, would that happen?
That one won't rearrange at all.
Why?
There's no way to get it to be tertiary.
Yeah, there isn't, but isn't there more hyperconjugation on this side?
Well, you're talking about too far away to do a rearrangement. You got to obey this statement. I know you want to move stuff from way over here and get a cation over there.
No.
Oh, you don't?
No. Just like you pre-visualize the p orbital,
Yeah.
and then we said that was hyperconjugation.
Well, yeah, this has got secondary hyperconjugation from both positions. Yeah. That's just definition of secondary. Doesn't help us here, though. I got to get to a better cation. So the only thing you know that's better than secondary right now is tertiary, right? So if you're not getting to tertiary from secondary, you're not doing it. Or if you start primary, you got to get to at least secondary, right? Primary to tertiary, that'd be great. I think we got a winner here, though. Is it an H or a C that moves? It's an H from the iso position, correct? There's an H over here. That H doesn't exist in the product. So there's your mechanism and there's your check mark saying yes. Why did it happen? Why or why not? Here, why not? C plus didn't get more stable. That's why it didn't work. So that's why the X. Why the check mark? C plus went from secondary to tertiary. That's a check mark, right? Got more stable. More stable. I'm liking the next one too. No, I don't like the next one. That's terrible. This is awful. I don't think I can have a big enough X for this one. It got worse. That's like major league X. Okay. So I'm going to have this comment with a telephone pole. So that's got the same telephone pole. C plus didn't get more stable. And this one will be a triple telephone pole when we need it. Okay, that's just short form, so I don't have to keep writing, okay? Oh, what moves in the next one down? It's not an H, is it? Yeah. We're supposed to show the mechanism even though it doesn't happen yet. Sorry about that. I got to read my own writing better. We're supposed to show it even though it doesn't happen. That would be the only way to do it, right? Got to take an H from that CH2. But on this one, what's moving this time? Carbon. Yeah, that methyl's down here now. Well, this is definitely just a straight up triple telephone pole, right? It went from secondary to tertiary. Same comment exactly, more stable. That's a check mark. And the next one, I think, is another check mark. We're going to move an ethyl group. That next one's nice. I'm going to put some numbers so you can see what's going on. Dude, I want the second one. Here, thank you. We got blue for numbers. Let's just, we can use the nomenclature numbers. 1, 2, 3, 4, 6. And the one with the methyls, that. The one with the diethyls, 1, 2, 3, 4, 5, 6. What bonds broke? I need two numbers that used to be bonded in the beginning and are not bonded in the end. 1 and 6. That is where you have to start your arrow. The bond between 1 and 6. How did he know? That bond does not exist in the product. The bond between 1 and 6. Where is 6 bonded to the product, in the product, and it wasn't bonded to it in the reactant, because that's where your arrow goes. So it goes from right between 1 and 6, and it ends at 2. Make sure it goes all the way to 2. 1 to 6 ends at 2. That will bond 6 to 2. 1 lost a bond and didn't get it back. So that's a cation. See, 1 is a cation now. And both of those are big time check marks. Secondary to tertiary, secondary to tertiary, double telephone pole, triple telephone pole. Yeah. Yes, we have a question. Okay, that's a great question. He asked why. He remembers from reading that cyclohexane is a little more stable than cyclopentane. He's correct, but that is only a subtle difference. So your ring is losing about 5% stability, not even. But going from secondary to tertiary is like a 300% improvement, right? It's not even linear at all. So that's why it was such a good question. The cyclopentane, almost no strain. Cyclohexane, absolutely no strain. What are the rings with strain? Because it's coming up right now. Remember strain? There's angle strain and torsional strain. Torsional strain because the ring is so small, you can't rotate the bonds. It's too rigid. It won't let you. So you're going to have eclipsing. That's ring size 4. That's coming up. And ring size 3. Those, forget about hyperconjugation. Those rings in themselves are unstable. So if you're not getting rid of those rings, don't do the rearrangement. Well, that's a big hint that even though this thing goes from secondary to tertiary, I don't care. This has excessive ring strain. There's two forms, angle plus torsional. Right. So when you moved the H from here to here, you thought it was good because you went from secondary to tertiary, but your ring is still too straight. This one, even though it goes from secondary to secondary, is still a great improvement in molecular stability because you went from a cyclobutane to a cyclopentane. You got rid of almost all the ring strain. Very little ring strain. So this secondary is more stable than the original. So it's not just about the hyperconjugation, right? There's other forms of strain that we have to remember from our past. That's why organic chemistry is so great. All the stuff you ever learned is relevant. Okay, and I think we got everything we need there. And yeah, stop share.